Good morning, everybody. Welcome. So we've been talking about energy, and up to now we've been talking about only about point particles. So we've been talking about point particles. So in the sense that we've talked about uh, gravitational forces and gravitational potential energy. And we've talked about electric forces and electric potential energy. But we've talked about systems where we've modeled things as point particles in the sense that they can't deform. They have no internal structure, then they can't get hot. But so we know we've talked about gravitational energy and the flow of energy between kinetic energy, say in an orbit, and gravitational potential energy increasing as kinetic energy decreases. And same for electric energy. But what we haven't talked about is energy inside extended objects. So what we need to talk about now is energy in extended objects. Because extended objects, solids, liquids, whatever, can get hot. And I think we know instinctively that getting hot, so when something is hotter, it means that there's more energy inside it. And so we have to be able to move from thinking about everything as point particles to thinking about objects that are made of lots of atoms and bonds, and look at energy inside these objects. And sort of here's what we're talking about. So here is our so here's our ball spring model of a solid. Except that up to now, we haven't really paid very much attention to the fact that these atoms, so that the balls represent atoms, the springs represent bonds. These atoms aren't necessarily sitting still. In fact, they aren't ever sitting still. So they're moving, and you can see that there's certainly kinetic energy in here, right? The atoms have mass and they're moving back and forth a little bit, so they clearly have kinetic energy. And it also seems that the springs must somehow be storing energy. Springs can be compressed or stretched, and then they can do work to make the atoms move. So if we consider the system to be everything, we need some kind of energy associated with these spring-like bonds. So in a certain sense, the energy in here is just the ordinary kind of energy that we've been talking about. There's kinetic energy. There should be potential energy associated with these bonds being stretched and compressed. And then there's rest energy. But when we have 10 to the 23rd atoms, it's going to be really awkward to try to find out exactly the speed of each one and the exact state of compression or extension of the bonds. So we need some more macroscopic way of describing and accounting for energy inside extended objects. And we typically refer to that as internal energy, even though it's not some new kind of energy. It's just microscopic kinetic and potential energy. That's actually all it is. But we need a way of talking about that. So what we need is to talk about potential energy associated with a spring. So and we're going to consider macroscopic springs first. And let's just think about an example of a simple horizontal mass spring system. So here's our spring, there's a mass, negligible friction. So this thing can oscillate, slide back and forth, stretching and compressing the spring. Okay, so it can go back and forth like that. Let's see if we could graph its displacement versus time. So we're going to start it out stretched. So initially stretched and release it from rest. And so it's at some maximum point here, and it's going to slide back towards its equilibrium position, okay, gaining speed, and it gains so much speed that so we're gonna say x is 0 when at equilibrium, just to make this simple. And so then it's going to be moving in the minus x direction, and then the plus x direction, and the minus x direction, and the plus x direction. And we saw actually that we could solve a differential equation, solve an equation using the instantaneous form of the momentum principle to get a graph of, to get an equation for this motion. So x of t was some amplitude, which is just the initial stretch, times the cosine of some frequency omega t. And it turned out we found that omega was the square root of the spring stiffness over the mass of the mass. And this is assuming an ideal mass spring system where the spring itself has negligible mass. So you don't have to worry about kinetic energy of the spring. All the kinetic energy just belongs to the mass. So in order to think about kinetic energy, we would want to graph its speed, or its x component of its velocity versus time. And of course, v sub x is just dx dt. It's the derivative of x versus t here. So we can figure out a few points. When it's at its maximum stretch, v is clearly 0. When it's at its maximum compression, v is also clearly 0. So we know that the graph of v sub x versus t is going to cross the axis at those points. So what's going to happen here? So if we started out stretched in the plus x direction, it's going to be moving in the minus x direction, isn't it? So v sub x will be negative until we got to there, and then it's going to be moving back in the plus x direction. Okay, so something like that. And now if we wanted to plot kinetic energy versus time, well, kinetic energy is proportional to v squared, right? Its kinetic energy is a half mv squared. And so let's see what we can think of here. So when v is 0, kinetic energy is clearly going to be 0. So the kinetic energy will be 0 at those points. Kinetic energy is always positive, however. So it looks like kinetic energy will be doing something like that, right? But if we consider the system of as the block plus the spring, then actually nothing in the surroundings is going to be the wall that it's attached to and the floor. Okay, we said that there was negligible friction, so we can neglect that. The wall is certainly exerting a force on the spring. Okay, when the spring is stretched, the wall is clearly exerting a force. But what's the displacement as the spring moves? What's the displacement of the attachment point of the spring at the wall? Okay, that point never moves, does it? So the work by the wall is actually going to be 0. So no displacement. So when we take the spring and the block as our system, we find that we need some sort of potential energy for this system. The wall is also not putting energy into the system, so it's clear the wall is not doing work and putting energy into the system. And so what has to be true of potential energy versus T? Can we sketch this on the same graph? What would that look like? So if this graph is kinetic energy, we'll just call this energy. So for this ideal spring, there's no way to lose energy. It's just going to oscillate back and forth. So presumably, the sum of kinetic and potential energy is going to stay constant again, just like in orbits. It's just that it's flowing back and forth from spring energy to kinetic energy. And so we want the potential energy to be some sort of a minimum when so potential energy should be a minimum when kinetic energy is a maximum, and it should be a maximum when kinetic energy is a minimum. And so we should get something that kind of looks like that. So let's keep that in mind. Now remember that the way we got equations for potential energy was that we worked out that the x component of a force was the negative gradient, the negative spatial derivative of the potential energy, right? We did it by taking antiderivatives. And so we know that negative k sub s times x, which is the x component of the force here, must have to equal negative du dx here. So let's think about what the form of the potential energy function has to be here. So here's our question. Which of these expressions correctly satisfies this requirement that minus du dx is minus k sub s times x. So the way I mean, one way to think about it, just try differentiating these things with respect to x and see if we get the right equation. And remember the minus sign. So most people voted for 4. And 4 is an attractive answer, but it actually isn't the right answer. It has the property that it makes potential energy negative, which is a good thing. But it actually doesn't work. So let's see why not. So let's just differentiate this, okay? So if it's minus, so ddx of minus k sub s x squared and there's a half here, is, so there's a 2 times minus a half k sub s x, which gives us a minus k sub s x, but we have to take the negative of that. So because f of x, fx is minus du dx, so that implies that fx is a minus k sub s x is plus k sub sx, which would mean that if you compress the spring, it wanted to compress itself more, and if you stretched it, it would want to stretch itself more. So that, in fact, doesn't work. But it would work if it was positive. So ddx of half k sub s x squared is going to be equal to a plus k sub s x, which means that fx is minus so in fact it's that equation. That's the answer. Now this is a very odd equation for potential energy. So if we graph this as a function of displacement, where again we're saying x equals 0 at, or actually let's just change it into s. We derived this saying that x was 0 at the equilibrium position, but a more general expression would be u spring is equal to a half k sub s squared plus some constant. Because it could be y, it could be z, it could be whatever direction. So, and that's a pretty odd plot for potential energy. So if we plot potential energy here, let's potential energy. So this is energy on the y-axis as a function of stretch. We're going to get a curve it's a parabola, isn't it? And it looks like that. Yeah, c is some constant here. It's the standard integration constant in calculus. It's capital C. The speed of light's a little c, but so modulo the constant, it looks like it's positive, which would mean there couldn't possibly be any bound states here. And now we can adjust that to some extent by just adding, making this constant be negative. So if we make the constant be less than 0, then it would shift this curve down, but at some point it would still end up being positive. So problems with it are, is U is always greater than 0, so no bound state, because K plus U is always greater than 0, and that can't be right because this mass spring oscillator is obviously bound. The mass isn't getting away from the spring. And it doesn't go to 0. U doesn't go to 0 as S goes to as separation goes to infinity. So this is some sort of weird ideal spring. And a real spring, it wouldn't work this way, because if you consider a real spring, if you stretch it too far, you get a straight wire and there isn't any force, and then you break the wire and then it's not bound. And if you compress it too far, then the force gets really, really, really big, because it's the coils of the spring are up against each other and whatnot. So this is some sort of ideal system and not a real system. And a real system would actually look a lot more like this. So for a real spring, we'd have we'd certainly, so we could have a region down here. So this is, again, this is stretch and this is energy. A region down here where, oops, wrong color. That looks parabolic here, like this, a half k sub SS squared. But then as it gets stretched too far, the spring stretches out and then it finally just breaks. And whereas if it gets too close together, then it gets very, very hard to push it together. So a real spring energy graph would look something like this. And we could call this distance here, this is our constant, E0 or E spring. It's a negative number so that we get bound states. So now we can have some bound states of K plus U less than 0. And it would kind of look like that. So this might be a kind of a helpful visualization here. So here's a Python program, which you can see in the demo programs at glowscript.org. But here's a different one. This one, there we go. So here is a potential energy curve where, again, the y-axis is energy and the x-axis is separation of something. And you can imagine a mass on a spring if you want. But we could visualize what would happen by picking a value of K plus U and thinking about, for example, a mass oscillating on a spring. So here the cyan arrow is momentum. And so large momentum, large velocity, large kinetic energy. And that magenta line also represents the kinetic energy at that instant. It's if the potential energy of the system is the green curve, then the magenta line is the K plus U minus U, so it's the kinetic energy. Now, if we give it a little more energy, it could oscillate back and forth here. And so those are bound states, but if we give it too much energy, then we get K plus U greater than 0, and then it disappears. Now, this is just kind of a fun program because you can actually draw your own potential energy curves. So we try to draw something like a parabola. We can see what happens. 4k plus u means k is higher at the center. You can also experiment with drawing some more interesting potential energy wells. Yeah, that I don't think you can, this is a function, so you can't actually make a loop, but we could see that, for example, something could get trapped in one region or another and not get there at all, and you'd need to give it more energy to get over that. So it kind of looks like reaction energy graphs for chemists. Anyway, you can make your own energy wells. But this particular energy well that we started with, where that represents a kind of our view of a real spring, actually has a name. It's called the Morse potential energy well. And it is a function that people have come up with to represent the potential energy between two neutral atoms bonded together with a spring. So exactly like these two atoms we've been thinking about inside our solid bonded together with a chemical bond. Okay. So the Morse potential energy actually has a kind of complicated equation. So the Morse potential energy to neutral atoms connected by covalent bond. And this is not something they're going to be required to memorize or work with, but you might be interested in the equation. So the Morse potential energy is a constant times 1 minus, this E is really E as in the base of the natural logs, to the minus alpha times separation minus the equilibrium separation. So this is the stretch, basically, squared minus. So it's this. We in fact do get this curve that we drew up here. Basically, that basically is the Morse potential energy. Now, when we solve spring problems using macroscopic springs, we're going to see that we probably are going to end up mostly just not even bothering to put in that additive constant because it's going to cancel out. So here, for example, is a spring problem that we could solve. Well, I'm not going to use it as a poll question. We'll work it out together. But here's the problem. We have a horizontal spring. It's got stiffness of 3 newtons per meter. It's got a relaxed length of 0.25 meters. The mass attached to it is 50 grams. And so you stretch it out. So initially, so it's this system. And initially, this is 0.29 meters. And then you release it with from rest, and it oscillates. And the question asks us, what's the kinetic energy when it goes back through this equilibrium position where stretch is 0? So let's just work it out. We can just use so it's an energy problem, so we just write out the energy principle, right? So we just say E final is E initial plus work. And the system is the spring and the block, and the surroundings, the only thing. Yeah, Joseph, that's right. So it doesn't have to be a covalent bond. I mean, there certainly are ionic bonds where the molecules that are bonded by ionic bonds, like HCl, which actually is a gas, absolutely do vibrate. So there's certainly potential energy in all bonds. So the surroundings is the wall. And notice that this point doesn't move, so the wall does no work. So that's 0. And so we have the initial state. So the initial state is stretched, and at rest, the final state is moving but relaxed. And so we have kinetic energy, so K final plus U final is K initial plus U initial. And we can write this a little bit, we can expand these things. So we have a half mv final squared plus a half K sub S final squared plus this constant. What do we decide to call it? E spring. Is equal to a half mv, that's right, initial squared plus a half K sub S initial squared plus E spring. And so we see that this additive constant we have here, the thing that, where this is E spring, this is S, and this is energy, it's just going to cancel out, okay, because that constant doesn't change. So we often end up not writing it. And now we see what else we can that we know is 0 in this equation. So the initial kinetic energy is 0 because it's at rest. And the final spring energy is 0 because the stretch is 0. So we have a half mv final squared plus is equal to a half K sub S initial squared. And actually, we're only asked for the kinetic energy, so we don't even really need to resolve that. So that's K final is equal to a half times the spring stiffness, which was, what was the spring stiffness? 3 newtons per meter, times the initial stretch, which was 0.29 minus 0.25 meters squared, which gives us 2.4 times 10 to the negative 3 joules. So again, energy problems are exactly the same, but all the work goes into, really all the work goes into this step here, into expanding out the This is where the action is. And to do that, you have to have picked a system, and you have to have picked initial and final states. Because so amplifying this meant because you picked the system, you knew the external work was 0. And then the initial and final states told you those two terms was 0. So all the thinking goes into this part, and then the rest is just solving, right? So let's think about this situation. We have a block that we're going to drop onto a vertical spring. And just imagine what's going to happen. The block is going to fall, compress the spring, go back up. Maybe it'll shoot up back up in the air again. Okay, so what is this ES constant? So what this ES constant really is here is this integration constant C. Okay. And we know it has to be a negative number. Okay, an integration constant can be a negative number, right? So we know it has to be a negative number because we know that the potential energy needs to be less than 0 for a bound system, so that we can have kinetic plus potential energy being less than 0. So this E spring ES constant is this negative number, and we'll see that for microscopic systems that number actually has some real meaning. We'll get to that when we talk about chapter 8. But it's this distance that the distance below the x-axis. And yes, this equation for this expression for spring potential energy, we treat just like another potential energy expression. So it's just like the gravitational potential energy expression, or it's just like the electric energy expression. So let's just set up this problem. Okay, we're dropping a block onto a vertical spring. And it's going to hit the spring, compress the spring, etc. And eventually, what we're going to do is we're going to ask some question about what the situation is when the block is 0.3 meters above the floor. Okay, and so the possible states we're considering here, and I think I really want. Yeah, okay, here. This is the version I want because I want you to answer this. So let's say we were asked to pick so the system is just going to be, well, let's pick, we're ahead of ourselves. Just consider the states. If the block is falling, and what we want to do, if the problem we're asked is find the speed of the block just before it contacts the spring, so when it's just there. Okay. What do we pick for the initial and final states? Okay. Okay, so you voted overwhelmingly for 1, which is right. So, good job. Why is it right? Well, because what we're trying to find out is the speed of the block just before it hits the spring, which means that has to be one of our states. So a rule of thumb for picking states is if you need information about some state, that's got to be one of your states. So we absolutely have to pick B as one of our states because we need information about that state. Now, the only other state we actually have any information about at the moment is A. So we would indeed need to pick A and B as our states. So let's just see how we'd set this up. We'd say, so indeed we want that. So the system is everything here. So this is the block, the spring, and the earth. So we have E final is E initial plus work, and since everything's inside the system, that's 0. So expanding that, we have K final plus U final equals K initial plus U initial. And now we have to be a little careful about what kinds of potential energy we have in this equation. So the thing that has the kinetic energy is the block, and it's moving already with some speed. So this is K final of the block. And now the potential energy, well, we have some gravitational potential energy in here. And remember that we can write near the Earth's surface, the gravitational potential energy is easiest to write as this minus g mass of the Earth over the radius of the Earth times the mass of the object plus an mgy. So it's the potential energy at the surface of the Earth plus the change in potential energy as you go above the surface of the Earth. And this thing is again going to be a constant that's not going to change. So we often don't even bother to put it in our equation. If we're compulsive, we can put it in the equation. So we can say K final plus a minus g mass of the Earth m over radius of the Earth plus an mgy final plus the u spring final is equal to K initial plus a minus g mass of the Earth, mass of the object of the radius of the Earth, plus mgy initial plus u spring initial. Well, the spring is neither stretched nor compressed in both these cases. It actually doesn't matter. So the spring potential energy is actually just going to be a 0. They're going to cancel out here, zeros. And this, of course, is a constant, and we don't need to write it out. And so what we really end up with here is we've got a half mv b final squared plus an mgy final is equal to a half mv initial squared plus mgy initial. And now we know all these values. So the question is, what is our unknown? And this is our unknown. So y final. We know the mass of the block, we know g, we know the final distance, that's going to be 0.04 meters, right? And here we know the initial speed, that's 2 meters per second. And we know the initial y, that's 0.8 meters. Not 0.04, 0.4. So we can solve for v final, and we get 3.44 meters per second, right? So here's exactly the same situation, except we want to find out something different. We want to find the speed of the block when it's now 0.3 meters above the floor, which means that the the spring is now actually compressed. So now the question is, what do we want to choose as the initial and final states for this situation? Okay, so the most popular answer was 2, but 3 was also a popular answer, and this time you're both right. Either one is actually okay. So if you said either 2 or 3, they're both possible. So the key is that C absolutely needs to be one of our states, because this is the state we need information about, right? So we have to pick. Now we can pick A as the initial state because we have all the information we need about A. We can pick B as the initial state because we actually just worked that out. So we now know how fast the block is. We know all the details of how fast the block is going just before the block hits the top of the spring. So we could do that either way. So either 2 or 3 would work for us. Let's just write out. I want to make this smaller here, so we can just set up the equations. So 2 or 3. So if we pick, we have to pick one, don't we? So that's the interesting thing about, so the question is, but now there's a spring force acting on the block, so doesn't that make something difficult? Because it isn't there the whole time. And the real beauty and simplicity of energy problems is that it doesn't matter what happens in between, you can solve energy problems just by looking at initial and final states and looking at differences. So if we take 2, so initial state is B, so initial, let's say I is state B, and final is state C. Then we still have the energy principle. We have E final is E initial plus work, and again, system is everything. And so leaving out constants here, so we're going to have K final. Ooh, it says my internet connection is unstable. I hope it's not very unstable. K final plus U final, U gravitation final plus U spring final is K initial plus UG initial plus U spring initial, because work is 0. And so we'd have the half mv final squared, and now the gravitational potential energy is still there, so we'd have this mgy final, and now we'd have the spring potential energy is non-zero, so it's a half k sub s squared is equal to the initial kinetic energy, a half mv initial squared plus mgy initial plus, in this case, 0 because the initial spring energy was 0 because it's not compressed, right? And so our unknown is V final here. And we know these quantities. We know Y final, that's 0.3 meters. We know the final stretch, so this is 0.4 minus 0.3 meters per S. We know the initial speed. What did we pick? We picked B, so the initial speed was whatever we got here, 3.44 meters per second. The initial Y was, so Y initial was 0.8 meters, and so we can solve for V final. If we pick 3, we have exactly the same terms, they just have different values. So we have a half mv final squared plus mgy final plus a half k sub s squared equals a half mv initial squared plus mgy initial plus, again, the spring energy is 0 because it's not compressed. It's just that we have different values. So this V is now 2 meters per second, and this is now, oh, that's not 0.8 meters in this stage, is it? This is just touching, so that was a 0.4 meters. That was wrong. Okay, this is 0.8 meters here. And these values are all the same. And I believe it works out too. You can check this by working it out yourselves. What I believe we get is, if we solve for V final, we get 2.7 meters per second. And you can also imagine a problem which actually defines the maximum height of the block. So the block bounces off the spring and goes up. So the key is just picking a system and sticking with it, picking initial and final states and sticking with them, and then just being really careful about enumerating all the terms in the energy equation. And you get where you need to go.